And now we're going to go into a different but related direction and look at the geoethics of geoengineering. Chris Tucker, our chairman, will lead this discussion. Chris?
This is awesome. I don't get to do this normally, like I get to do the planning and the glad handing and whatever, but I actually get to do a panel, and this is really fun for me. I didn't even come up with this topic. AGS counselor Bob Chen, who spent, 30 years with Columbia's climate school and the Earth Institute before that, put this topic on our agenda, and then they said, who wants to do this panel? And I raised my hand. So there's a lot of different ways that we could talk about the geoethics of geoengineering. We're cutting a very specific slice through this conversation, just so you know. We're not covering everything because you can't do it in 50 minutes. So what I wanted to do is kind of focus in on a topic that's near and dear to my heart with some people that I really enjoy having these conversations with, and I think you will enjoy this conversation. I've got Dr. Ken Bisler, senior scientist at Woods Hole Oceanographic Institute. So if you know anything about oceanography, that's where the rock stars of oceanography hang out. There's some other places, but just letting you know. And then we have Miss Romany Webb, who's deputy director here at Columbia University at the Sabin Center for Climate Change Law. And she's a total rock star too. They have been living in a space that we're going to talk about called ocean iron fertilization. There's no reason you should have ever heard of it, but we're going to kind of get into it in a fun way. So I'll go, I've never used the slide thing here, so there we go. So I decided I'd start this with just some infographics that I saw in the newspaper because it was actually helpful to me. There's a lot of words around making the world a better place and dealing with climate, et cetera. A lot of people talk about climate mitigation because bad things are going to happen. How do we make them less bad? Some people talk about climate adaptation. Things are going to go bad, so how do we adapt? Some people talk about climate restoration. What can we do to actually bring ourselves back to the climate that we had previously? And one of the big topics here is carbon dioxide removal, right? And there's many forms of it that are out there. You'll read it in the news. It's very confusing, but these graphics made it easy for me. So here's one, right? You can read about it. This is actually trapping CO2 putting it back where it came from, right? Where the dinosaurs were once upon a time. There's multiple versions of this. One is called direct air capture. And you'll read it in the news that somehow we're going to have these magical things that pull the CO2 out of the air, and again, you got to put it somewhere, put it back where the dinosaurs came from. Here's one. It's different, right? This is just trying to cool it by sending the sunlight back, right? And you could spray sulfur dioxide up there. There's some other ideas out there like marine cloud brightening. For just putting saltwater mist up there, kind of a similar effect. I didn't even know about this one, but apparently glaciers actually melt from the bottom. And what if you can actually prevent the warmer water from getting there with a whole bunch of air bubbles? I have no idea how they're going to generate the energy to do that or how they'd engineer that, but I don't know, it's somebody's idea, and it might be a good one for all I know. But then they had this one. I said, oh, Ken, you got to see this. You got to see this article. Ocean iron fertilization doesn't get talked about that much. And the reason I wanted to actually focus this conversation on it is because of this year's theme. This year's theme, right, is cooperation and conflict in a changing climate. And to do many of these CDR approaches require some real cooperation to pull this off. And some of them don't, like direct air capture. I guess somebody builds a thing and it just works. It turns out it's super expensive. We don't know if it's ever going to work at scale. But this particular one, I think, is a really fantastic case of 35 years of great refereed science out there that Ken's going to be able to talk about. Actual open ocean experiments that have occurred under an international regime of treaties and protocols that Romany will be able to talk to us about. And then we're just going to have a freewheeling conversation about this, and we are going to do our best to get to some Q&A from the audience. So I know that's a weird intro, but I think you're going to see it as soon as Ken gets up here with his beautiful maps. Come on up, Ken.
All right, thank you, Chris, for that introduction, and thank you all for listening to an oceanographer. I use maps. I mean, I was thinking at this meeting, every time I go out to sea, I go on ships. First thing I do, I pull out a map. I also look in the vertical, right? So my maps have another dimension to them. But we're looking at water properties, physical properties, and in this case, we're going to be talking about some changes to ocean properties that would come about if we wanted to do what nature does, which is adds a micronutrient called iron. So we're going to get right into it. I've only got 10 slides, and we saw variations on this type of plot before. I'm using it to remind us of two things. I think someone yesterday said we should get the emissions curve down to zero. Not sure we'll ever get it to zero. We know it's been going up. But if you look at our emissions, we're at about 40 billion tons. And so I'll be using gigatons, GT, sometimes on these plots. But that's a lot. We'll get into how big is a gigaton on the next couple of slides. But we know how that dark gray, how we might, with current technologies, reduce those emissions, right? There's political, there's economic reasons why we might not be doing it, but we know how to do that. The blue part, we really don't know as much about. That's some of the crazy things Chris was showing. How do you suck carbon dioxide that we've already emitted out of the atmosphere? We already are experiencing the consequences of having put too much CO2 in the atmosphere, other greenhouse gases, but predominantly carbon dioxide. So we've got to come up with a way to remove, if you look at that scale, on order 10 billion tons of carbon dioxide or its equivalent out each year from the atmosphere. I'll show you one of those methods. But for almost all of these, we really haven't progressed very far. Can we reach net zero by 2050? That's going to depend a lot more on our emissions reduction than the increase of negative emissions or carbon dioxide removal. But that needs to come along. And we have a few years and some hope that if we applied both of these, we could get to a net zero point and also reduce what's already in the atmosphere. That's quite important. Even if we were not to emit another atom of carbon dioxide, we still have to get back to where we were. So this is a nice, fun question. How much is a gigaton? How much is a billion tons? And so one way I've been thinking about this, you can look at elephants, aircraft carriers, well, coal cars, they carry carbon, right? About 15 meters long. Each coal car carries about 100 tons of carbon equivalent, a little less than that. And humans, over the course of our history, have released 400 billion tons, gigatons in carbon units, 1,500 in carbon dioxide units. So think of a train that you see going by, all those cars, it's getting slow, it's going by. It's trying to carry 1 billion tons. Well, that coal car, if it were at the equator and you could do it, it would have to circle the planet 4 times. So that's what 1 billion ton of carrying capacity would be for a train. This is an enormous amount. We've released 400 of those, and so we've got a big problem. We've got to figure out what to do. Well, the next question, where does all that CO2 go? Some we know goes in the atmosphere, about a third, some on land, some in the ocean. But here's the optimistic thing. Already the oceans, we said 400 on that last slide, there's 37,000 gigatons in the ocean interior. So all of human emissions, if they were to be stuck down there, would change that number by 1%. That's the biggest active reservoir for storing carbon on this planet. So there is really no solution to our climate crisis without considering the ocean. You have to consider that. It's a much bigger reservoir than, say, all of the land plants, all of the soils. So anything we do in that environment, we know it's about 50 times more than the atmosphere, and we're trying to get it out of the atmosphere. That's our problem. I put blue carbon up there. There are great reasons to protect our coastal resources and increase mangrove swamps and salt marshes and things, but it's just not a big enough place to change the dial on climate. But the ocean interior is. So now we have to think about how we're going to do that. What's it going to take to get more of the carbon out of the atmosphere and into the ocean? I was fortunate, the start of my COVID quarantining, I was part of a virtual academies committee, National Academy of Sciences, and we were given a task, Romney was on the same committee, to say, hey, these are 6 ways to do it. What do we know? What's the research agenda that we would need? I worked mostly on the chapter about ocean iron because I've been doing this for a while. It's part of my research since the early 90s, really. And one thing you probably don't know, a couple things maybe, oceans are full of plants. Half the oxygen on this planet comes from the plants in the ocean, not on land. Those plants need sunlight, they need nitrogen, they need phosphorus, but they also need a small amount of iron to grow. And so what we were experimenting with back in the early 90s, early 2000s, is could we go out and manipulate the ocean and increase plant growth by adding this, we call it a micronutrient, the elemental form of iron, and seeing if we could kind of juice up this biology. And then, in fact, that's what we did. It's very clearly evident here. Can't get much clearer than that picture in the middle. That's a true picture of the water in the Southern Ocean before and after iron was added in the last US experiment. It turns green. The plants grow. Plants are microscopic. It's a beautiful image of a Chaetoceros. It's a diatom. These plants happen to have silica shells. They grow quite fast. And as we'll see on the next slide, they sink quite efficiently. And we were pretty excited because we could see our experiments from space. This is an early satellite picture, a different experiment, but that horseshoe shape on the right, that's the chlorophyll as seen from space, about 100-kilometer scale bar on there. So just by adding 1 ton of iron, we got several thousand tons of carbon leaving the surface ocean. So that was very exciting. This proved John Martin, if you've ever heard of John Martin, very famous oceanographer, said, give me half a tanker of iron, I'll give you the next ice age. That was his quote. And so completely successfully, we showed that. But 20 years ago, we didn't have the wherewithal, the time, the funding technology to really say, where does that carbon go? Because if we're going to impact on longer time scales, this uptake of carbon dioxide from the atmosphere into the plants, right, photosynthesis, we need to know how deep does it get. And I'll show you a map a little bit later, but exactly where you'd have to get it, how deep you'd have to get it. But the idea is we put an iron at the top, right? We get things to grow in that surface layer where there's sunlight. We call that the euphotic zone. And then some of that carbon starts its way down. That could be a dead plant itself, the diatoms that sink as they aggregate when they run out of something else. Usually it's silica that they use to grow. That could be the animals that eat them, the zooplankton that eat the phytoplankton. They produce fecal pellets. So I spend a lot of time talking about poop. I usually put that up on the slide. Kids love it, but it's basically the marine snowfall that carries the carbon out into the plants, but it's going to carry it deep enough. And the importance there is as these particles settle, you can start locking away that carbon for centuries and millennia. We don't have to bury it under the seafloor. We just have to get it deep enough. And I'll show you how deep. But that's really the key unanswered question, because people I often get asked, why are we doing this again? Well, we never got to the answer. We'd have to stay longer. We'd have to make bigger perturbations and have technology out now. We have remote underwater vehicles that we can leave behind. I would go out sometimes 30, 40 days, but that's about the limit of a research ship at sea. So that hasn't changed, but we have a lot of ways to monitor this. That's where we're going to try and get to. So here's a few maps for this audience. You know, we looked at this map. This is actually what John Martin was looking at when he had that hypothesis, because he was looking at the concentration here of nitrate, the form of nitrogen in seawater at the surface, and there had been hypotheses about why is there excess, why is there more of that dark color around Antarctica, up there in the Pacific, northern Pacific, some of these upwelling regions. Well, basically, those are the places that have low iron. Iron typically comes from dust. Antarctica is the simplest example to think about. It's a continent that's covered in ice, right? So there's not a lot of dust being generated. So those waters are particularly fruitful. Although the X's, they're white and red on this particular slide, are where the past experiments were. And we went to those areas. We call them high nutrient, low chlorophyll, because they have low chlorophyll, low plant biomass, but high nitrate. And indeed, that's where it works best. There's a star there in the central Pacific. There's some evidence that we might actually stimulate plants or that perform nitrogen fixation, so you can take nitrogen out of the atmosphere, fix that and grow on that. So that could happen, but it's a lot less well studied, but we think that's also possible. But some of the scaling I'm going to talk about is all about these high nutrient areas. We talked about how deep, well, we talked about the centuries and millennial time scale. So I want to get this carbon out of our system for at least 100 years. That's kind of what markets are looking towards. That's kind of something on a scale that might affect several generations on our planet, might help us from reaching certain tipping points. Yes, it'd be great to go longer, but this is a map where the color gives you how deep those sinking particles, my marine snow, would have to be locked away for 100 years or more. And you'll see a lot of that in blue as soon as you start getting to some of the lighter blue shades. It's like 500 meters, 1,000 meters. It's really not that deep. Oceans go often 3,000, 4,000 meters deep. So you don't have to get it all the way to the bottom to lock it away. And this map is created by physical oceanographers who know the timescales of the return, circulation, the mixing of the ocean. And that's calibrated pretty precisely based on things like anthropogenic release of tritium through bomb testing or freons in the atmosphere. We go and measure those as chemical oceanographers to say how long has that water been there. So we know this pretty well. That's a map that's been very helpful. And then two more just examples of Mother Nature, because we did this on that scale of 100 kilometers and 1 ton. Well, when you have a volcanic event, this one, Kasatoshi, it's probably hard to see. Oops, didn't want to do that. How do you go back? Look at that. I was trying to point, it's the Aleutian Island chains, and what's coming off of it is the ash on the top image, a satellite image. That one in the middle is just chlorophyll. This is a satellite image of the plants that grew in response to that. This is August of 2008. And you won't be able to see all the details on the graph at the bottom, but someone had, by chance, a sensor in the ocean that measured the drawdown of carbon dioxide, that's the red line going down, and the increase in pH that goes along with that. So we very easily could show that that event had something like 10 million tons of carbon were exported in that particular short-term event in August. So we know this works in nature. Another example were the Australian wildfires that happened December, January, kind of 2019, 2020 that we were all watching, and some of these horrific images coming over the TV. Basically, people right away realized that's a lot of carbon getting out into the atmosphere, right? You burn down a tree. Well, the lower maps, they go from Australia, New Zealand on the left and South America on the right. One is tracking where the ash went, and the other one on the bottom is, again, a chlorophyll image. The response of the ocean was to grow more plants. So almost on a one-for-one basis, the amount of carbon dioxide released was taken back into the ocean by the plants that grew in response. We don't quite know how much got deep or sequestered, but it's something like 150 to 300 million tons. So now we're getting up to a fraction of a gigaton. This is significant. This is pretty short term. There were no negative effects. People weren't going through there and seeing dead fish, other things. This is what nature does all the time. So we have some optimism. So I'm getting near the end. I just want to reemphasize that for iron fertilization, one of the many, someone said this morning, it's not a silver bullet, it's silver buckshot. This is probably not the only way we would manipulate or choose to manipulate if we decide to go this way, the ocean. But it does scale, certainly up to something like 4 gigatons of carbon dioxide per year. We had estimates less than 1 to greater than 4. That's considering the high nutrient areas on that map, that yellow-orange band. A little iron goes a long way. We've shown already in our experiments that it just took 1 ton of iron to get 1,000 tons, actually several thousand tons of carbon out. That number in nature is like 100,000. I think the new experiments, we can probably cut that or increase it by a factor of 10. And that's one reason that it's going to be cheap. I'm using sunlight for power. Iron is a super abundant mineral. The amount of iron you need to do this will perturb natural production by less than 1%. It's really a trivial amount of iron, and there are a lot of companies, people coming to us all the time, say, I've got this waste product, can you take it and put it in the ocean? So I think that's why it's going to, we also don't have to build a factory like a direct air capture site, right? We're just putting this behind a ship or flying an aerial drone to disperse the iron. And then we have experience here. We've done this 13 times. We did not observe direct harm, but we did see things turning green. Nature has been doing this. I didn't talk about the glacial, interglacial records, but a lot of evidence points to iron as being one of the controls of those cycles that have been happening. And we know we got about 4,000 tons out of SOFEX, the last US experiment. If people have been following direct air capture news, Iceland, I think they got 2,000 or 1,000 tons after they wanted to scale that up. I mean, we did this really unintentionally about 10, 20 years ago now. So the last thing I just wanted to leave you with, and we'll have time for discussion too, is that we've formed a group, the Oceans Commons. This is done mostly in the high seas. Romney's going to talk about some of those laws, how you would permit this, who would control that. So we've brought together kind of a bottom-up formation of a group of scientists, academics, some commercial people from now 37 institutions in 9 countries to form this EXOIS, Exploring Ocean Iron Solutions. We don't have the solution. We're exploring if it works or not, where you might do this, how you might scale it. We're looking at the efficiency of the carbon, but also very interested in the ecological impacts. What else can happen? What can go wrong? And there are a lot of things we need to be measuring. So these are not trivial experiments. You got to bring the right team together, and I think we've got that team. We're housed at the Woods Hole Oceanographic Institution where I work, but I'm completely independent to do what our group wants to do, and we're certainly at the point where we're looking for partnerships for the science, for the funding, and just to bring this to fruition. So with that, I think I'll pass it on to Romney.
All right. Good afternoon, everybody. So I wanted to talk, I'm just setting a timer here so I don't talk all day. I'm going to talk about some of the governance considerations that go along with these activities. And I am going to talk about ocean iron fertilization, but I'm also going to talk a little bit more broadly about the field of ocean-based or marine carbon dioxide removal. Because as Ken mentioned, ocean iron fertilization is just one of several ocean-based carbon removal techniques that's currently being discussed. There are research proposals. In some cases, there is commercial activity happening in this space. And so it's worth looking sort of across the field. I'm going to talk specifically about international governance because, as Ken said, we're talking about doing things in the ocean, and the ocean is, of course, an internationally shared resource. So as many of you will know, generally speaking, coastal countries, those that border the ocean, have primary authority over areas near to their shores, usually within 200 nautical miles of their shores. But areas further offshore, the sort of dark blue in this graphic, are what are sometimes referred to as the high seas or international waters, where no one country has jurisdiction or control. And those areas are open to use by all countries in accordance with international law. There are, sort of generally speaking, 2 broad bodies of international law that are especially important to think about when we're talking about ocean-based carbon dioxide removal. One is the global climate change regime. And the foundation of that regime is the UNFCCC, the United Nations Framework Convention on Climate Change. It was passed in 1992, and it is really a hugely important and foundational treaty in the climate space. It set the overarching goal of stabilizing atmospheric greenhouse gas concentrations at a level that would prevent dangerous anthropogenic interference with the climate system. And under the structure created by the UNFCCC, developed countries were expected to take the lead in achieving that goal, and they were to do that both by reducing their greenhouse gas emissions and protecting and enhancing greenhouse gas sinks and reservoirs. And the UNFCCC adopts a really broad definition of sink that refers to any process, activity, or mechanism that removes a greenhouse gas from the atmosphere. That includes all of these CDR techniques that we've been talking about, everything from direct air capture to ocean iron fertilization. So from the very beginning, from the 90s, the global climate change regime has, at least implicitly, approved of the use of these techniques to mitigate climate change. And support for CDR within the global climate change regime has only grown since then. One notable thing about the Paris Agreement is that it codified the idea of net zero. It talks specifically about countries achieving a balance between greenhouse gas emissions from sources and removals by sinks. And so there again, you see this reference to removal and this support for removals. And that support has only grown in recent years. Repeatedly, over the last couple of years, the parties have emphasized the role of oceans and marine ecosystems as greenhouse gas sinks, and they've called for various sort of actions to accelerate carbon dioxide removal generally and marine carbon dioxide removal specifically. What you don't see in the global climate change regime is sort of detailed rules that would control when, where, and how we actually do these things. And that's really important because, as Ken said, these activities may have unintended or intended consequences that need to be managed. And so we do need a set of rules to control where and how they occur. There have been attempts to develop those rules in the context of other international treaty regimes. There are currently no binding international agreements that deal specifically with CDR generally, and ocean CDR in particular. But we do have lots of international agreements that generally apply to ocean-based activities, and that could have implications for ocean ion fertilization or other marine CDR techniques, and you see some of them on this slide. The parties to some of these international agreements have looked specifically at marine carbon dioxide removal and, in particular, ocean ion fertilization. And so I want to talk about the history here in the context specifically of a set of international agreements called the London Convention and London Protocol. Very briefly, the London Convention and the London Protocol both regulate what's called ocean dumping. The convention was adopted first in the 1970s, and then in the 1990s there was an effort to sort of modernize and update this treaty regime, and so the London Protocol was adopted. The idea is that the protocol will eventually replace the convention, but so far not enough countries have signed on to the protocol. So the two operate effectively in parallel. They both, as I said, regulate ocean dumping, which is defined to mean the deliberate disposal of waste or other matter in the ocean. And for the last 15 years or so, there's been an ongoing debate about whether ocean ion fertilization in particular, but also other marine CDR techniques qualify as dumping, whether they can be viewed as a deliberate disposal of waste or other matter in the ocean. The parties first started talking about this in 2007, and the reason they started talking about this was that in that year, there was a proposal by a US-based company called Planktos to do a fairly large ocean ion fertilization project off the coast of the Galapagos Islands. They were planning to use a US-registered vessel for that project, and so the US Environmental Protection Agency conducted a review and said, actually, we think that this activity will be regulated under a domestic statute that implements the London Convention. Planktos responded in various negative ways and ultimately said that they were going to use a foreign vessel to avoid US regulation. That ultimately didn't happen because the project couldn't get financing, but it set off this sort of firestorm at the international level, and we continue to see the effects of that today. So the US referred the matter of ocean fertilization to the parties to the London Convention and Protocol. They conducted a review and they said, yes, actually, we think this activity does fall within the scope of those conventions. And they adopted a specific resolution on ocean fertilization that basically said, these activities present risks. We may allow some research, but there should be no deployment. The parties sort of doubled down on that approach in 2010, and there were some follow-up actions. Then, if you fast forward to 2012, some of you may remember that there was a large ocean fertilization project off the west coast of Canada conducted by the Haida Salmon Restoration Corporation. The stated purpose of that project was to restore salmon populations off the west coast of Vancouver Island, but the company was also selling carbon credits from this project. This generated a huge amount of controversy. There were many scientists who said, this is completely inappropriate, we can't track what's happening to the carbon, so we shouldn't be selling carbon credits. There were environmental groups that were very concerned about the potential environmental impacts and the lack of monitoring for those impacts. The Canadian government conducted a review and ultimately decided not to take any action, but again, the international community looked at the issue and they adopted a formal amendment on what's called marine geoengineering. I'm not going to spend a lot of time on this because I imagine there's maybe one lawyer in the room, and I don't want all your eyes to glaze over, but it's actually really important. This 2013 amendment says, you see here, contracting parties, so that's countries that have signed on to the London Protocol, shall not allow the placement of matter into the sea for marine geoengineering activities listed in Annex 4 unless the listing provides that the activity may be permitted. So if we break this down, we're talking about putting stuff in the ocean in connection with a marine geoengineering activity. The definition of marine geoengineering is actually very broad, would capture really all of these CDR techniques that we've been talking about. But a marine geoengineering activity is only covered if it's listed. And currently, only ocean fertilization is listed. And the amendment says that permits may be issued for ocean fertilization projects that involve legitimate scientific research, but not for any other activities, including any deployments. So deployment is not allowed under this framework. Now, this amendment was adopted over 10 years ago now. It has still not entered into force because it hasn't been ratified by enough countries. But it is hugely influential, and actually the parties, I'm going to come back to that in a sec. The parties have said that they think this same approach should be applied with respect to other ocean-based carbon dioxide removal techniques. So things like ocean alkalinity enhancement, that's getting a lot of interest at the moment, should be treated similarly. Allow legitimate scientific research, but prevent deployment. Now, I think on its face, this approach seems to make sense. Ken talked about the previous work that's been done around ocean fertilization and the remaining unanswered questions there are around, about that approach and the need for more research in this space. So why not allow this research to happen while restricting deployment? The challenge, or at least one of the challenges, is how to distinguish research from deployment. Because, again, as Ken said, in order to test these things in a robust way, we need to go into the field and we need to do relatively large-scale, long-duration projects which start to look a lot like deployments. And so the dividing line between research and deployment becomes really difficult to draw. The parties have tried to help with that by adopting what they call an assessment framework for evaluating research projects. And part of this is an initial assessment to figure out if a project has proper scientific attributes to be considered legitimate scientific research. And they've identified basically 4 criteria for something to qualify as legitimate scientific research. We actually don't have a lot of experience applying these criteria because they've only been applied in a couple of instances. But those couple of instances suggest that the parties are going to take a really strict approach and only allow research in very limited circumstances. So there was one project that was approved by Iceland last year under this framework, and when the Icelandic government reported that they had approved this project at a meeting of the parties to the London Convention and Protocol, they got a lot of pushback from other delegates and other groups who said, hang on, the project you're permitting is really large. Surely that's too large to be considered scientific research. And that's really interesting to me because on this list of criteria for what qualifies as legitimate scientific research, there's nothing about size. So it suggests that the parties are really taking a very strict view, a very narrow view of what should qualify here. So why is that? It is clear that the parties are quite skeptical of the benefits of ocean ion fertilization in particular, and also other ocean-based carbon dioxide removal techniques. Many parties do not think that it works. I was on a panel earlier this week with the guy who represents Germany in meetings of the parties to the London Convention and Protocol, and he was very skeptical as to whether this had any climate benefits or any broader environmental benefits. So that's one thing. The other thing is that the parties are very concerned about the risks that accompany these activities. And they've had, over the last couple of years, this sort of ongoing debate about whether they should be balancing potential benefits against potential risks. And many of the parties have actually said, no, we shouldn't be doing that. We should only be considering the risks that these activities present. And you see that here. This is a report from a meeting of the parties that was held last year. And they said, some of the delegations said they could not support the consideration of benefits as the aim of the London Protocol is marine environmental protection in favor of the precautionary approach. And so this is sort of a good example of the precautionary principle in action. The precautionary principle is a principle, a sort of long-standing foundational principle of international environmental law. The best known articulation of it is in the Rio Declaration from 1992. And Principle 15 of the Rio Declaration says that where there are threats of serious or irreversible damage, lack of full scientific certainty should not be used as a reason for postponing cost-effective measures to prevent that damage. So in the context of the London Convention and Protocol, the parties are applying this precautionary approach to justify really quite significant restrictions on ocean iron fertilization and other ocean CDR techniques, even in the context of research. But you could actually also apply the precautionary principle in the other way to actually justify moving ahead with those activities. And so you see a version of the precautionary principle actually in Article 3 of the United Nations Framework Convention on Climate Change, which talks about parties taking precautionary measures to address climate change. And it says, you see at the bottom here, where there are threats of serious or irreversible damage, lack of full scientific certainty should not be used as a reason for postponing those precautionary measures. So if we accept that at this point climate change is causing serious and irreversible damage, then this provision says really we should be doing everything we can to address this problem, including potentially moving forward with at least research into some of these activities. So I would argue that the precautionary principle is actually not that helpful a decision-making framework in this context because it can be applied in these sort of contradictory ways. And we really need to rethink the way we govern these activities that could be, we don't yet know, but could be an important part of our climate mitigation toolkit, but also need to be governed and regulated in a way that minimizes the potential for any adverse impacts. That's all I had. I'll leave it there. Yeah.
I love that. I don't know about you. You clap, so I'm assuming you love that too. So I want to start with just kind of you talking a little bit about the geography of the ocean. I mean, a lot of people go, oh, the ocean. And I know AP Human Geography, do you guys even teach the ocean a little bit? So, right, humans have co-evolved with the oceans for, our entire existence, but, right, mostly in coastal areas, right, because we live mostly on land. And the ocean isn't one place, right? It's like an agglomeration of a bunch of different ocean ecoregions. They all have their own ocean chemistry, their own biological processes. Can you talk a little bit more about that? Because you talked about depth and you talked about like nitrogen, but right, we don't want to screw all that goodness up.
Right, I mean, and there are, maybe you want to divide them into the physical features, like a Gulf Stream that can separate waters to the north that are colder from the south, carry that heat over to Europe, influencing their climate, and there's questions, could that shut down if temperature gradients change and things like that? So there are huge physical boundaries that we deal with all the time, and there's studies that go through those into the water below them and trying to measure the tracers, the transients, the things that follow that water. I think I mentioned tritium and freons. So there's a whole cadre of mapping of physical features, and that gets down to smaller and smaller scales. It's called the mesoscale, the sub-mesoscale. Now people are making models on the few meters kind of scales, and that's pretty essential given all the complexities of some of those movements. And then biologically, warm and cold waters have very different biological communities, very different seasonality. As you had ice-covered regions, that area of ocean, Antarctica, it expands by kind of a factor 2 in the winter when it's covered in ice. The ice retreats, things just take off. They get the sunlight they need. They get the right growing conditions. And so the biology responds. And that marine snow, you think it's so easy, just measure these particles as they settle, right? Well, one how do you do it? Traditionally, you put basically a cup in the ocean and collect stuff that falls into it, a sediment trap it's called. But that flux varies from day to night, location to location. And so these biological responses to these physical forcing and light ultimately at the top really change then those particles which affect the whole chemistry. I'm in a chemistry department, and one of the programs is called Geo-Traces, crosses the middle of those ocean basins to measure every chemical property that we can, not just iron, but cadmium, cobalt, all of those, to learn about those distributions. So we're just getting better at making the maps across large swaths for all of these processes, and now we're bringing in molecular biological tools and others. So it's a pretty exciting time, actually, for mapping these large-scale distributions and layering them on top of each other.
Awesome. And I do want to say we got about 20 more minutes, so if you do have questions, feel free to line up. I'm just going to throw them out until I see some people with questions. So, Romani, I wanted to ask kind of, a few years back, our theme was the ocean. Sorry you missed that one. And our AGS counselor, Dr. Christopher Linden, the other oceanographer in the house. How many oceanographers in the house? 2, right? 2. Thank you for your service. We actually had Kim Stanley Robinson, the author, the science fiction author. He had just released Ministry of the Future, and that started with a massive heat event in India, killing 20 million people, a work of fiction. But then that kicked off all these IPCC type mechanisms, and they started thinking about the precautionary principle in a very different way in the book. So I guess I'd ask, if I could frame it this way, right? If the climate crisis keeps getting worse, which I'm just going to say is kind of inevitable, at what point does like a Manhattan Project mentality versus a decadal scale, longitudinal, scientific, exercise, if the urgency flips, how do these international cooperation regimes deal with that?
I mean, I think it's very challenging because international law generally is not particularly adaptable. Things tend to move slow. We have a very siloed system where the same countries may participate in negotiations under the UNFCCC and the London Convention and Protocol, but they're represented by different individuals and departments. There may not be a lot of sort of cross-pollination between those regimes. And I think that has been a real issue in the CDR space in particular, because we see the global climate change regime like forging ahead to support these activities as much as they possibly can, and then we see these other regimes really putting on the brakes. And so I think part of the answer to your question is like, how do you break down those silos and promote those sort of cross-regime collaborations? I do think that the new BB&J treaty, the Biodiversity Beyond National Jurisdictions Treaty, that was the text of which was agreed last year, it hasn't entered into force yet. If that ever enters into force, which is a question in my mind, but if it does, I think that could actually be very useful in this regard because it creates a number of different structures that really facilitate this sort of intergovernmental engagement on these sorts of topics. And so that's one place. I think we might see it in some other places as well, but I do think like the structure and general turtle pace of the regimes is very much a challenge.
Excellent. Sir, at the microphone.
I've got a two-part question. You quickly mentioned pH. I know from the ocean pH that I know there's a lot of concern already about the carbonation or about adding carbon. I'm adding carbon to the ocean and creating pH problems. Why would this iron fertilization not cause that? And then on the flip side, I was also wondering. I know there's a lot of issues. There's a lot of nitrate issues with the fertilizer runoff in the.
These are great questions.
In the Bay of Bengal and the Caribbean. Could the iron fertilization potentially address those issues as well?
The 400 dead zones in our ocean. These are great questions.
Great questions. The first one about adding. Someone said you shouldn't add another atom of CO2 to the ocean. There's too much already. Yes, the surface ocean is acidified. One of the reasons coral reefs, shellfish are suffering is because of the ocean acidity, the extra carbon dioxide, right? That gets pushed into the atmosphere because there's pushed into the ocean because there's more in the atmosphere. What these techniques do is they get it out of that surface layer. If you reduce the concentration in the atmosphere, we will reduce ocean acidification, period. What we're doing is we're sticking that deep enough that we won't experience that acidification. I kind of sometimes joke, if you want to save the Great Barrier Reef, you got to get that carbon down deep, right? If we're going to save coral reefs, we've got to get it out of the atmosphere. We've got to reduce that acidification. As far as the nitrogen loading, those areas that were orange and red on my map, they're perfectly healthy. It's not a eutrophication. It's not something, this is a natural, well, most of the areas that were blue, they don't have a lot of nitrogen, but these aren't the dead zones. These are healthy, productive oceans around Antarctica that happen to have, we call it excess nitrogen, a very different situation than toxic blooms and other things that we don't want to see happen. But we will look for that. I mean, these are legitimate questions that as we scale up, do we reach those points? We know, people worry about oxygen being depleted. There's just no way we can put another gigaton, well, you can see how big that reservoir is in the ocean per year and not influence the oxygen balance by more than a few percent. So I'm not worried about some of the things of those concerns, but as a scientist, we will measure everything. Measure the shit out of it, as Chris likes to say.
I like to say measure the shit out of it. Yeah. So I'd like to point out in the audience here, one of our colleagues, Peter Rabley, who's now the president, CEO of the Open Geospatial Consortium. When he was at Omidyar Network, he started the Ethical Geo initiative at the American Geographical Society, which then spawned with our friend, I think Denise is still here, Denise McKenzie. We had an international team that launched the Locust Charter, which is an international set of principles for the ethical use of geospatial data. The reason I say that is I want you to talk a little bit about MERV, right? Monitoring, reporting, and verification, what that means, what the technologies are, CMERV versus eMERV. And the reason I say that is because you probably think of it as oceanographic data, and we think of it as geospatial data. And we're focused on the ethical use of that geospatial data that you probably consider oceanographic data. And that ties back to everything you were just talking about. Is it an experiment or is it operations? Well, if I'm using my MERV every day, is it okay to scale up? So anyways, kind of to both of you, maybe you first, Ken?
Well, the MERV, so MRV, Monitoring, Reporting, Verification, I think it was the Washington Post, one of the major newspapers called it the 3 most important letters in CDR, carbon dioxide removal. But the attention early on was the companies are spreading. We haven't really talked about the commercialization that's going on right now. So companies, there's a lot of venture capital coming this, and to them, MRV really is carbon. It's what you can monetize. You can sell a carbon credit, so I want to have technology and models to do that. And we think for the oceans you can. It's challenging. Yes, water moves, so I've got to have instruments that move with the water. But we know how to do that. What we've been trying to introduce with EXOIS, the group I'm in, is EMRV, a small e for the environmental and ecological consequences. Because those are sometimes harder to measure, but maybe more important reasons for not doing something is the environmental harm, the other greenhouse gases, things that can come along. So
that might occur in one part of the ocean, but not occur in another part of the ocean.
Or with one deployment scheme or one scale of deployment. So we're really always talking about MRV and EMRV, but it's hard to monetize that. And I think that has to be set by whoever's paying the bill, right? You don't pay for those credits unless they can show that they've done both of those things.
And the cost of the science has to be built into the cost of the credit, right?
Yeah. Who's paying for that?
Right,
Yeah.
right.
Yeah.
I would just say that I think the commercialization of the space really creates some challenges when we're thinking about this, because if we're measuring for environmental and ecological impacts, we want that data to be publicly available. Similarly, the carbon data, we want that to be publicly available so that we can vet what these people are doing and say that it achieves, see that it achieves what they say it's achieving. The challenge with commercialization is IP. And so how do you balance those competing goals? Recognizing that the private sector and private finance will likely be really important to scaling this field. So I think there's some tension there.
Last question.
Hi, Thank you. Can you hear me? Yes? Question for Ken, I think. In following the conversation for deep ocean carbon sequestration, what is the effect on benthic communities, or what studies have been done for that?
Right now, experiments, I'd say there's zero. There's just not enough perturbation of that system. That volcanic ash, we kind of look to nature. We look around islands that are sources of iron from their coastline, and you see healthy benthic ecosystems in these areas that have higher iron input. But yes, we have to think about not just the impacts at the surface, but the midwater and all the way. But at the scales we're talking, we already have 10 billion tons of carbon, 40 equivalent, leaving the surface ocean with those sinking particles already. So if I make 10 into 11, I don't think I'm going to, well, I think I'm going to be removing a lot of carbon, which is good, and therefore the consequences on the bottom, which will be small, I think will be worth it. So we are also trying to compare, this gets back to the precautionary principle, what we're doing versus doing nothing. Some of the concern I have is if we continue to do nothing, we're in trouble. And we've got to get rid of the mess we've already created in addition to reducing our sources.
Thank you. I'll say a couple parting comments. Check out oceaniron.org, one of the best nerd websites I've ever seen. All the science, really accessible, show it to the kids. It's really fantastic, the work that your team has done. And people have said, in previous panels, right, what can I do? How do I get involved? This is an international community. You don't need to be a world-leading scientist to be a fanboy or fangirl of what these folks are doing, and hold them to task, right? Keep their feet to the fire on eMERV and all the environmental consequences. But I just want to thank you for all your great work, and thanks for coming and joining us today. Please give them a hand.